Okay, hello everyone. Welcome to the final presentation of the of our design class on heat exhaust and diverter design in the ARC conceptual fusion reactor. This is the 2263 fusion engineering class, design class. There are the students over here, and I'll get going. So, the point of the beginning of this is to give you the background as to what we established as the ground rules for the class at the beginning. So the starting point of this was the ARC conceptual design. There was actually the result, in fact, of the last version of 2263. Here's the pictures that everyone's quite familiar with. It's a very compact 500 megawatt fusion device using HTS-based magnets, has demountable toroidal field coils. And in terms of, for this class, the size was in fact fixed at a major radius of 3.2 meters. And in fact, down here, was in some sense the beginning of the class, that we established a physics scenario that produced 500 megawatts of fusion. It's a rather compact device. How would you actually exhaust the power in this? And that's why, in fact, that there's a question mark on this. So the goal was design the detailed vacuum vessel and diverter for heat exhaust and ARC. So here again was the up-close picture. Well, actually, I'll start over here. Here's the up-close picture of how it was conceived. In fact, you can see that there's very little detail to no detail, in fact, at all, about the diverter regions, which are this part and that top up and the bottom, which are dedicated to heat and particle exhaust. There was some slight consideration of internal circulation of the molten salt immersion blanket, high temperature molten salt, through the vacuum vessel for heat removal and nuclear heating, but that was it. The other feature of this, which I've zoomed in here a little bit, is because of the demountable coils, internal coils in red, which are normal coils, and in green, which are superconducting, were allowed inside of the TF coils, which is a feature which is allowed when you have demountable coils, so that you can in fact put those rings inside of those. So these were allowed in the design class, and that was basically the cartoon that the students started from at the beginning of it. That was the only thing that we said. We suggested some aspects of design innovation, and in fact, for the starting points, but like a good design, it wasn't clear about where these were going to go. Here are the two major innovations. One of them was actually in terms of the diverter topology or magnetic topology that was going to be allowed. This is an idea that was in fact come up by Brian Bombard here at MIT, with the idea that here's the standard primary null point that produces high performance core plasmas. You bring down a diverter leg, and then in fact by an internal, in this case, set of internal coils distributed in ADX, you were able to produce a null point, another poloidal null point that is very far away from that X point, and therefore through this actually be able to establish a controlled detached plasma and dissipated plasma that would result in large amounts of radiated power around it. And this is a result of a simulation by Maxime Umansky at Livermore. So we basically said, let's try to make this magnetic topology in this. And the other part of this was to use additive manufacturing, namely the capabilities. And here you can see a real component with some complex internal structure, which is actually made out of steel. And there were some initial modeling results led by Rui Vieira that, in fact, adding in these was going to enhance heat exhaust. But these were left, in fact, to the students. I just want to point out is that a key educational point of the class is that the students become familiar with sort of modern engineering, computational engineering design tools. And all the results you will see, even though they can't go into the details of this, were in fact vetted, in fact done through these calculations. Neutronics are done with MCMP, the magnetic equilibrium with ACOMI, heat transfer and internal stresses with COMSOL, and there's also some dynamic E&M response, which is also done with COMSOL. And the students will not describe those because those are actually well-known tools. So finally, this class literally would have been impossible with my travel schedule and my other duties without a very large team teaching effort. This is very much a team effort. Brian Bombard, who was critical, in fact, of course, with his expertise in diverter physics and ACOMI. Dan Brunner helped immensely with his ideas about instrumentation and diverter materials exhaust. Brandon, who was in fact a member of the 2263, the last one design class, helped immensely in the neutronics. Rui Vieira in heat transfer and other aspects of this. And a special note actually to Chris Lochman and Pierce Grover from Mitsubishi Electric Research Laboratory. that they embedded themselves in this class and were just immensely helpful to many things, particularly about the console modeling with heat exhaust and sensors. So thank you very much for that. And others did this. Just thank you for me for all your help. Okay, so enough of me yapping. Let's get going on into the design class.
Thank you, Professor. So on the left, you can see a poloidal cross-section of the original ARC design. As you can see, there isn't a ton of detail around the diverters. It's a relatively rough sketch, although it still has a lot of the main components there. On the right, you can see an Akomi design that represents exactly what we've produced through this class. Let's see, you've got so we believe that our work has enabled us to determine that the pathways exist to increase the fusion power of the arc reactor substantially. We've done a lot of thermal loading calculations and neutronic simulations, and we believe we might be able to get the fusion power up to about 1 gigawatt. And here in this next slide, I'll be able to show you exactly what we've done. So for starters, we've been using superconducting coils. That was one of the main attractions of ARC because it uses less power to maintain the plasma. We've run more detailed simulations, and first of all, the superconducting coils are these rectangles with the X's on them. And we have been able to produce a proper diverter equilibrium while adequately shielding them to ensure a relatively long lifetime. We have both a double null and X-point target diverter, which enables a stable detachment front and adequate thermal loading. So for the starters, when I refer to the diverter, I refer to this circle. I do not refer to this leg, which I'm going to talk about in a sec. The diverter leg, actually, we have, in several iterations of the design, we have extended the leg to increase the amount of neutron shielding for the diverter, which has actually produced a 10-fold reduction in diverter neutron flux. Finally, through all of this, we've been able to still maintain a tritium breeding ratio of about 1.08. As Professor Whyte had mentioned, we have been experimenting with 3D printed vacuum vessel technologies in order to create embedded cooling channels and maintain structural support of the vacuum vessel. And finally, we have conceptualized and explored the area of remote performance monitoring because, well, we don't want the reactor to melt. So one of the key innovations of this class was the realization that FLI, our coolant, is both visible through a few light spectrums and non-conductive, which enables us to optically sense details about the plasma, including fusion power rate, temperature, magnetic sensing, and all sorts of other information with sensors, many of which are outside of the vacuum vessel. Okay, so this is a general outline of the 4 main topics that we tackled in this class. We looked at the magnetic design of the reactor, we looked at neutronics, and actually conducted some real MCNP simulations. We looked at the diverter thermal design, and finally, we looked into diagnostic sensing and control. Without further ado, I pass it off to Alex Freely to discuss the magnetic design.
Good afternoon, everyone. My name is Alex, and today I'll be talking about the magnetic design of our new ARC diverter set, as well as the coils that we're using to create this design. So to start off with, an X-point target diverter with a balanced double null is compatible with the original ARC geometry and plasma parameters. So just to start off with, this is a poloidal slice of the ARC reactor. So this is just looking at one poloidal piece for those of you who aren't as familiar with tokamak engineering drawings. Just a quick reload, and this is about 1 meter up here just for a sense of scale. Diverter coils are both these upper and lower orange boxes here with X's. The vacuum vessel is in the center here. The fly tank is out here with the light blue filling it in. And I can show you the balanced double null is represented by there's upper and lower null in the magnetic field. And the X-point target is this second magnetic null in both of the diverters. So the original ARC plasma parameters had a plasma current of 8 megaamps, an elongation of 1.8, and a triangularity of 0.375. these parameters were maintained in this new design, while at the same time enabling this much larger diverter volume and this X-point target diverter. Engineering parameters, major radius of 3.3 meters and the vacuum vessel surrounded by fly. And in this new diverter geometry, we have the diverter X-point at about 3.7 meters. And by having this long leg and the diverter X-point, this helps stabilize the detachment front that Dennis talked about a little bit earlier in the presentation, which allows radiative heat transfer rather than all of our heat going into a strike point on the diverter. So as a quick cartoon of what this detachment front would look like, bringing it back from the ADX design earlier to our ARC design here, this long leg X-point target diverter stabilizes the detachment front and allows for radiative heating, as I just said. So essentially we'd have a detachment front somewhere in this diverter leg pushing up against this diverter X-point in the diverter volume. So I'll talk now a little bit about the actual coil set that we're using and to show you that these are actually reasonable parameters and reasonable coils that we've been able to design. So the full magnetic equilibrium for the diverter has been achieved with superconducting coils outside of the fly tank. And this is something kind of new that we looked at because you don't actually need any copper coils inside the fly for the equilibrium magnetic field. And this is really nice because it allows you to significantly reduce your power consumption for your diverter coils and also to shield these coils from the neutrons being generated in the plasma. So for each, the upper and the lower diverter, we have three main diverter coils. We have an inner diverter pole coil, an upper outer diverter pole coil, and a lower outer diverter pole coil. So these are they all have about 4 or 5 megaamps of current in them. And so this seems like a lot of current, but the critical current density of this YBCO is actually quite high. However, this does present a design trade-off that we have to look at. So the superconducting coils are sized to allow vertical removal of the vacuum vessel while still operating below the critical current density. So as Dennis mentioned at the very beginning of the presentation, the TF coils, the toroidal field coils, are detachable. And one of the big advantages of that is that means you can take the entire vacuum vessel and lift it out vertically from arc. And this allows you to replace the vacuum vessel and other internal components without taking everything apart and having like undo all of your TF coils and everything. But in order to maintain this ability, this means that all of our superconducting coils here had to be radially either inside the inboard side or outside the outboard side of the vacuum vessel. So these two vertical lines represent the inner and outermost extent of the vacuum vessel. And as you can see, all three of our coils are far enough away from the vacuum vessel that this entire vacuum vessel can be removed vertically without having to move these coils. And so, as I said, the YBCO, or the high temperature superconductor critical current density, depends on both magnetic field magnitude and direction with respect to the coil. This YBCO is actually a great improvement over previous superconducting technology. As you can see, on this inner coil, we have a toroidal field of 19 Tesla and a poloidal field of 1 Tesla. On these outer coils, it's about 7 and 3 Tesla. And most superconductors wouldn't operate at all or very, very little in these types of fields. But with YBCO, this inner coil is about 1/6 of the critical current density, and these two outer coils are at about 2/3 of the critical current density. In addition to our equilibrium superconducting coils, we also have low current copper trim coils inside of the fly tank that can adjust to magnetic geometry on fast time scales. So the diverter X-point we've found is sensitive to plasma current changes of about plus or minus 2%. So if your plasma current, your main plasma current, starts to change by about 2%, this diverter X-point will either start to move around or you may develop a strike point. However, because of this, we must be able to correct magnetics on fast time scales. So what we've done is we've added trim coils, both the diverter trim coil and vertical stability coils, inside the fly tank. And the reason we do this is that so the field from these coils can propagate into the diverter or into the plasma on fast time scales. So it's about 50 milliseconds. This is because there's less Inconel or steel, essentially, between the coils and the plasma. And the fact that fly is non-conducting really helps out with this because it means that fly is low conducting, I should say. It doesn't inhibit the propagation of the field from the coil to the plasma. In addition, the trim coils are close to the plasma, which means that they can use far lower currents. So just as a comparison, the plasma has about 8 megaamps. The diverter coils have 4 or 5 megaamps, whereas the trim coils and stability coils can run at about 0.02 megaamps. This also means that they only draw about 25 kilowatts of power because they're running a fairly low current. Finally, this is jumping a little bit. I'll explain this diagram. We also looked at the mechanical forces on all of the coils. And it turns out that the Hoopt forces on the magnetic coils and the vertical forces between coils are all safely within stress limits. So this is a 3D von Mises stress simulations of the full coil set. So this is the diverter coils, which are here and there. So this is the outer and inner ones, plus the central solenoid, which is a big cylinder in the middle. And the vertical equilibrium coils. So these are these 4 coils furthest on the outside. These weren't fully part of our design, but these were kind of set by the original ARC design just to determine like the overall magnetic geometry. But we needed to include all of the coils in these presentations, in these simulations, in order to make sure that we were getting the right total magnetic fields and stresses. It turns out that the peak von Mises stress from Hoopt tension is about 80 megapascals. Which is far below the stress limit of these materials, which is somewhere on the order of 800 megapascals. In addition, the vertical forces between the adjacent outer diverter coils, so these 2 coils here and the lower ones there, those have high currents running in opposite directions, so they tend to push each other apart. These forces are high. It's a total of about 260 meganewtons for the whole coil, but can easily be counteracted with a reasonable support structure between the coils, because it's actually a fairly large total surface area. So I've talked a little bit about the magnetic design and the coil set that we are planning on using in our new ARC design. And now I'll turn it over to Jake, who will talk about neutronic simulations and of the shielding of the coils.
Thank you, Alex. So the part of this project that Max and I worked on had to do with turning the original ARC MCNP model, which you see at left, into what we have on the right. So what we were trying to do is update the kind of general cartoon model of the vacuum vessel, which is based on just a elliptical toroid, into something that reflects at least the vast majority of the complexity of our new vacuum vessel and of our new diverter geometry. In order to do this, we had to develop a tool that would take outputs from a Comey, or just sets of points that define a geometry, and turn them into something that MCNP could understand. The way this was done is we wrote a MATLAB script that takes the points along here and turns them into macro bodies, which MCNP can then interpret as shapes that or as closed volumes that it can transport neutrons through. The advantage of having this tool was that we could not only capture the vast majority of the complexity of the design, and that we've got a multi-layered wall here, we've got shielding, superconducting coils, but that we could also rapidly iterate. So if we ran a simulation, got an output, realized that, say, our superconducting coils were getting too many fast neutrons, we could very rapidly go back to the magnetics design, look at a way to change that in a Comey, and then come back here and generate a new MCNP input and see if that's changed the neutron flux. One of the main outputs of this process was the fact that we needed additional shielding for our superconducting coils. So this inner pull coil, for example, down here, without shielding and with the same fly tank design, only survived about a year using a rough estimate for lifetime of 3 × 10⁸ neutrons per square centimeter. This is a very conservative estimate, by the way. It's just the limit of what past research has gone to. But regardless, this was lower than we would have liked. So what we had to do was add in a very hydrogen-rich material to slow down the fast neutrons hitting it. So in this model over here, we've got about a factor of 5 improvement, and that's from the addition of 25 centimeters of zirconium hydride shielding. The main result of this was that we were actually able to uprate the total power that ARC could make and still have superconducting coils that have a lifetime equivalent to that of the toroidal field coils. In addition, the extended leg diverter design that the magnetics folks came up with provides a big advantage in terms of damage rates to high heat flux materials. So DPA is kind of a measurement of radiation damage, it's displacements per atom. And the DPA rate of the high heat flux materials down here in the diverter significantly lower. The reason that is that there's basically no line of sight from the core plasma to these high heat flux materials that doesn't go through a significant amount of FLIBE. This softens the neutron spectrum and therefore lowers the DPA rate. In addition, this brings down the helium to DPA ratio, which is a bit of a measure of the flux or the spectrum hardness. And that means that we can test some of the diverter materials a bit more easily. Unfortunately, they weren't low enough to where we could test in a fission-based facility. The flux is just still slightly too hard. Those 14 MeV neutrons are just very difficult to slow down, but it's moving in the right direction. As I said, the neutron flux that you see in the diverter is significantly softer. What we've got here in blue is a plot of the neutron flux at the midplane, scaled up times 50, so you can see it on the same chart. And that is compared to the neutron flux in the midplane. So we've got diverter down here in blue, midplane in kind of orange. And as you can see, there are a lot more neutrons in the diverter at lower energies. And the height of this peak corresponding to the primary neutrons, the ones at 14 MeV, that's significantly lower. Adding FLIBE just really slows them down quite quickly. Still, as I mentioned earlier, the inner pull coil is what's limiting the lifetime of our design right now. So while it is equivalent to the toroidal field coil in terms of lifetime, this is a new result and it's something that we can change going forward. So despite adding 25 centimeters of shielding, we're still at about 5 years total lifetime. In the future, we can change the thickness of the shielding, perhaps change the geometry or the exact position of the coil, and give us a slightly better result, hopefully. Now, this 5-year lifetime, as I said, comes from a very conservative estimate. And I believe someone in this room is actually going to be doing research on that topic. And it's possible that, that 3 times 10 to the 18 is nowhere near the actual limit of these coils. In addition, despite the fact that we vastly increased the amount of surface area of the vacuum vessel, we did not significantly change the tritium breeding ratio. So in the last ARC paper, if you recall, the tritium breeding ratio was about 1.1. Well, when we came back to this design and ran those same calculations, we discovered that TBR was about 1.08. This is good. This means that we make more tritium than we burn, and that's important. Part of the reason that we're able to do such a thing is because our coolant and our neutron breeding material are the same thing. They're FLIBE. And we put FLIBE right here. This is, so the white you see here is the inner vacuum vessel. There's a beryllium multiplier, which is kind of the greenish color, and then there's the outer vacuum vessel. Well, there's a layer of FLIBE in there designed to cool the inner vacuum vessel. And because it's in a region of such high flux, and the flux is at such a high energy, it makes a ton of tritium. So actually like 26% of the total tritium is made in this very, very thin layer. What you see at left is a plot of basically where tritium is made within the FLIBE. And basically, most of it is made in this very thin layer outside of the main vacuum vessel. This means that even though we've added in this shielding here, which is sucking up neutrons that could otherwise be used to make tritium, it hasn't significantly impacted the amount of tritium that we can make. Next, we're going to be moving on to diverter thermal design.
Thank you, Dick. So I will be covering the diverter thermal design, which includes the overall pumping design of ARC, as well as the cooling channel design that we use for active cooling purposes. So first, to give you a sense of what the heating challenges of ARC are, ARC generates, for 1 gigawatt design, ARC would generate 1.2 gigawatts of thermal power. 83% of that power comes out as volumetric heating from neutron interactions and also exothermic nuclear reactions. And the rest comes out as surface radiated heating, which hits the vacuum vessel walls and diverter walls. And that's shown at the top and bottom here, respectively. Again, in the ARC design, fluid FLIBE serves both as a neutron blanket, coolant, and tritium breeding site. And so that means immediately 620 megawatts of this neutron heating is exhausted directly into the coolant. And so that significantly, that makes the cooling problem significantly easier to deal with. Finally, because of our long leg diverter design that stretches out to, again, 3.7 meters, we have a very large area to work with. And when combined with the radiative strike point, brings down the average heat flux in the diverter to 3 megawatts per meter squared. So to give you an idea, an overview of how the cooling system is designed, on the right here is a picture of, again, the reactor with pipes overlaid. And on the left here is a schematic design, showing the same parts. So from the heat exchanger, we have cool fly being directly pumped from this heat exchanger to active cooling channels, which surround the vacuum vessel. Again, the heat exchanger going to the active cooling channels on the left there. Additionally, we have in dark blue, we have a additional overflow pipe that allows for independent control. Of the flow through the heat exchanger and through the active cooling channels. And then finally, once the fly has taken up the heating from the reactor, it leaves again to the heat exchanger through the big red pipe there. So one big advantage of our design here is that there are no moving components in the fly tank and no flow through vacuum. So all of our pumps here that provide flow through the cooling channels are outside of the fly tank, and so they're outside of the neutron, the high neutron fluxes and such. And if you needed to maintain them, you wouldn't have to drain the fly tank. Additionally, because fly is a molten salt, it has a melting point of around 730 Kelvin. We have to operate at high temperatures. In particular, we designed around an inlet temperature, a cold temperature of 800 Kelvin, that then leaves at around 880 Kelvin. And these high temperatures are good for thermal efficiency, for converting the thermal energy into electric energy. And finally, we have very manageable flow parameters. The total flow rate is 3.3 cubic meters per second. Flow speeds are about 2 meters per second through the entire system. And the entire pressure drop through the system is only 12 atmospheres. So moving on to the design of the active cooling channels, what is shown here on the right is a slice of the diverter cooling channels. On the top, we have 12 we designed for a 12 megawatt per meter squared heat flux. And so this is 4 times the average heat flux that we expect to see. And this is for margin and also possible peaking factors. This 12 megawatts per meter squared hits a first wall material, which we explored either tungsten or TZM. Immediately behind this first wall is a cooling channel. And again, these cooling channels surround the diverter and travel colloidally and have 2 meter per second fly flowing through them. And finally, behind this cooling channel, we have 4 centimeters of structural inconel, which all then sits in the bulk fly tank, which is sitting at around 880 Kelvin. So the main challenges we addressed in designing the cooling channels were what the channel geometry should be, what the pumping power required to cool this entire system would be, what the peak temperatures we would see are they within manageable limits, and finally, what are the thermal stresses that we expect to see. So to give you an idea of what has already been done, ITER has a tungsten water-cooled swirl tube diverter design that they've begun to build mock-ups of and test. And they've managed to build a tungsten mock-up here, shown on the right, with, again, internal swirl tubes that can survive 1,000 thermal cycles at 15 megawatts per meter squared. So this is already exceeding our design goal. Because we are using FLIBE, we ran CFD simulations and showed that FLIBE can achieve similar turbulent heat transfer properties as water. So again, using 2 meter per second FLIBE at 800 Kelvin, we achieved a turbulent heat transfer coefficient, H, of about 200,000. There's a slight caveat here where FLIBE has, while it has a low conductivity, it still has some finite amount of conductivity. And so there's some MHD effects that may reduce this number based on some experimental tests of analogous conductivity water. We believe that there could be up to a 30% reduction in the turbulent heat transfer. And so we applied, to be conservative, we applied a 30% reduction to our H all across the board. But this would be an area of future research. But so using this reduced value of H, we get a temperature jump from the bulk to boundary of 70 Kelvin, which is pretty good. And finally, a pressure drop of 350 kilopascals per meter. And in order to get a swirl tube design like this, we looked into 3D printing. And so 3D printing would allow for these kind of complex interwoven geometries to be made out of materials that you couldn't traditionally manufacture these complex shapes out of, such as tungsten, which is very difficult to work with. In particular, one application of 3D printing that we were looking at was the use of these open cell metal foams. And so some of the results that I'll show you in the following slides will also include a kind of speculative shaped open cell metal foam that could achieve similar turbulent mixing as a swirl tube while remaining isotropic in its properties. So first, to cover the pumping power requirements, do these swirl tubes? How much power do these swirl tubes require? So it turns out, again, based on our CFD simulations, only 1.5 megawatts of pumping power is required, of fluid pumping power, would be required to push the fluid through all of these channels here. Comparing this to the 1.2 gigawatt thermal output of ARC, it's a pretty negligible fraction there. Additionally, to give you a sense, the circulation pipes, which bring the FLIBE to the cooling channels, easily fit through the tank openings between the TF coils. And these medium-sized pipes that you see on the left there, to give you a sense of how big they are, these are 16 centimeters in diameter. And the big one there is 34 centimeters in diameter, so a little over a foot. Now, moving on to the solid components of the cooling channel design, these requirements are mostly driven by the materials that we choose for the first wall, for the diverter first wall. So in looking for materials that would serve as suitable first wall materials, we were primarily interested in two figures of merit: the thermal shock resistance, which is the maximum stress that the material can take, divided by the linear thermal stress. And we were also interested in the thermal performance, which is a function of the thermal conductivity, K, as well as the maximum temperature that the material could take, which is represented as delta T max here. So going back to Jake's slides, again, a unique advantage of the long leg diverter is that material in the long leg diverter would take 10 times less neutron damage than material in the vacuum vessel. And so this makes the materials choice selection enormously easier. We don't have to deal with we're dealing with an order of magnitude reduction on the neutron fluxes compared to the vacuum vessel. Additionally, another unique feature of the ARC design is that because it operates at 800 Kelvin steady state, we operate well above the ductile to brittle transition temperatures of irradiated tungsten, which sits around 500 Kelvin. So these lead us to believe that tungsten and possibly TZM, which is an alloy of molybdenum, for those that don't know, could serve as viable first wall materials. And so tungsten here, shown as a gold circle, just barely meets the minimum requirement for a thermal shock, while it does very well from a pure temperature standpoint. And we've identified 3 paths to kind of meeting our desired requirements. One would be an isotopically enriched TZM, because normal TZM has issues with neutron activation. And so if there was some way to select only the isotopes of molybdenum that don't have neutron activation issues, we'd be able to use it. As well as a tungsten alloy, somewhat along the lines of TZM, so an enhanced ductility tungsten, or possibly a tungsten foam with some secondary high materials such as copper for increasing thermal conductivity. So using that, we proceeded our analysis using TZM and tungsten. And so we performed 3 simulations of heat transfer and stress, and showed that the peak temperatures are well within bounds. So using 875 Kelvin FLIBE, which is what we expect the hottest FLIBE in our system to be at, and 12 megawatt per meter squared heat flux, which again is 4 times the average heat flux we expect to see, we get peak temperatures of 1500 Kelvin with the swirl tube design, and around 1300 Kelvin for this kind of swirl foam design. And again, one of the benefits of this 3D printed material would be that we don't have these localized hotspots from geometric effects. Comparing these temperatures to the maximum steady state temperatures, which should be around the recrystallization temperatures of TZM, which is around 1650 Kelvin, and tungsten, 1550 Kelvin, we see that we have lots of margin to proceed from a temperature standpoint. However, from a thermal stress standpoint, the thermal stresses are high enough to begin to enter a plastic deformation regime. And so from an 800 Kelvin strain reference temperature, so expansion from the coldest steady state operating temperature, we expect to see peak stresses of around 1300 megapascal with the swirl tube design. And again, these peak stresses are due to geometric effects of the swirl tube, versus around 700 megapascal using some sort of isotropic foam material. Comparing these to the yield stresses of TZM and tungsten at the operating temperatures that we expect to see, these do exceed the yield stresses. However, looking at the linear strain that the simulation returned, the linear strain was only around 6.4 times 10 to the negative 3. And when we compare this to the uniaxial strain to failure of irradiated TZM and tungsten, this strain seems to be well within the bounds of how much tungsten and TZM can stretch and pull at these temperatures. And finally, we began building a global model of the vacuum vessel. So on the left here, we imported the entire vacuum vessel geometry into COMSOL. And then from there, we set up a thermal stress simulation with the swirl tube geometry. And this global simulation agrees with the results of our local simulation. And again, we get peak stresses of around 1,000 megapascal and concentrated hotspots and concentrated stress due to the swirl tube geometry. So in summary, we've shown that the diverters are close. Current materials science is very close to providing us with a diverter design that can exhaust 1 gigawatt of thermal power from ARC. Thank you. And now I will, Libby Tolman will present to you the sensing and control work that we've done.
So we've just outlined for you a system to manage heat fluxes in ARC. But for this system to operate in an actual reactor, you'll need a set of sensors that will allow you to control it. And there are a few issues that you run into when you try to design this set of sensors. ARC will have a much higher neutron field than devices like CMOD, so some diagnostics just won't work on ARC. If you have any diagnostic with a window, that window could become blackened by neutrons and no longer work. You also have the big FLIBE tank there, and you don't want to put too many things in the FLIBE because it's quite hot, quite corrosive, and you also don't want to eat into your tritium breeding ratio so much. So you want to do as much of the sensing as possible remotely. Luckily, we have a big advantage when we're designing such a remote sensing system, and that's that FLIBE is mostly transparent. So we could actually look into the FLIBE and get a lot of information about what's going on in the reactor by doing that. As we mentioned before, FLIBE is also very, very slightly conductive, which means that you can get magnetic signals out from the plasma much more quickly than you would if you were dealing with a conductive blanket. So I'm going to lay out for you the sensing system we've designed on a high level right now, and then we'll go through each of the sensors in more detail. Our first set of sensors are so-called hotspots that will line the edge of the diverter and its leg. And these hotspots will be areas of the diverter that will heat up in response to things that are happening on the inside of the diverter. And these heated up regions will black body radiate through the transparent FLIBE to an imaging system. Now, depending on the neutron sensitivity of your imaging system, it may have to be located behind an additional FLIBE standoff with reflective optics. But eventually the black body radiation from your hotspots will get to the imaging system, and you'll be able to tell how hot your diverter is by looking at that radiation. The next set of diagnostics is a mid-plane imaging system that's going to look at Cherenkov radiation. Many of you are probably familiar with Cherenkov radiation. It's seen quite often in fission reactors, and it's this beautiful blue glow that you see here. And that glow, the intensity of it will be proportional to the neutron power in ARC. So by sensing the intensity of your Cherenkov radiation, you'll be able to get a measure of how fast your reaction is going. The next set of sensors are reflectometers. Now, we've talked a little bit earlier about how we're going to be running in ARC with this ionization front that is a little bit up the leg of the diverter. And the reflectometers, which are symbolized here by their waveguides, will allow you to tell where that ionization front is. And by sensing that position, you'll be able to get some understanding of how your plasma is behaving and also to control it. The final set of sensors are shielded magnetic sensors, which will sit outside the FLIBE tank. And these will allow you to detect small changes in the magnetic equilibrium. All right, we'll start by talking about the hotspots. You should remember that the diverter of ARC is ringed by cooling channels. So if you didn't have hotspots, you wouldn't get any information about the temperature on the inside of the diverter out to the outside because you have the cooling channels carrying away that heat. And the hotspots are designed to take that information from the inside of the diverter and bring it out. So you see in the image over here, the cooling channel that goes along the diverter is right here. And this yellow section is the inside part of the diverter that's facing the plasma heat flux. And this conical structure goes through the cooling channel and goes out to the bulk FLIBE. So as your heat flux of the plasma changes, this part of the hotspot will change its temperature. And the black body radiation from that part of the hotspot will travel out through this cone and out to the main FLIBE tank, where you can pick it up with your imaging system. Now, we've done some simulations of how this structure will respond to a step change in heat flux. In this case, we're taking the heat flux that's right here, and we're starting with the 12 megawatts per meter squared that Norman discussed, and we're stepping it suddenly to 24 megawatts per meter squared. And this is designed to give us some sort of understanding of how quickly the structure will respond to sudden changes in the plasma. So in this plot over here, we have on the x-axis the distance along this little line right there. That's the part of the hotspot that will be imaged by your blackbody imaging system. And at point A, you have the point that is at the bulk flibe tank, and at point B, you have the plasma-facing area. And so we put on the increased heat flux, and then we watch what happens to the structure at 10 millisecond time intervals. So you see the temperature here is on the y-axis, and when you set the heat flux, you see a temperature change almost immediately at the plasma-facing area, as you would expect, but it takes actually around 40 milliseconds for any information to get out to the point where you would image it with the blackbody spectrum. And the change in temperature there is smaller than the change you see at the plasma-facing part. But this change is still enough for us to be able to detect changes. And to understand why we'll be able to image the blackbody spectrum of these hotspots with the flibe, we have to know a little bit about flibe's optical properties. You see up here an image of flibe from Wikipedia, both in its solid form and its liquid form. It's important to note that this flibe is actually doped with uranium, which gives it this like greenish color. Our flibe will not have that greenish color, but it will still have this transparent appearance that you see there. One of the issues that we ran into in designing the sensing system is that most experiments with flibe have actually been done with very small quantities, like the quantity that you see here. And that means that over long scales, like about a meter, the optical properties of flibe are simply not documented. But by talking with people who work quite often with molten salts, we were able to come up with what we think is a reasonable model. You see that in my second bullet point here. At wavelengths below 2 microns, we're saying that flibe has an absorption coefficient of roughly 1 inverse meter. So you'll have some absorption, but not too much. And at longer wavelengths, above 2 microns, the flibe will be completely absorptive and you won't be able to get any information out. Now, that is a bit of a constraint when you're imaging blackbody spectrums, because blackbodies are, of course, stronger at longer wavelengths, but we still think you'll be able to get enough information out. So we ran some numbers with a sample imaging system that looks around 1 micron, and we looked at a hotspot change from 1100 Kelvin to 1120. And that leads to a change in radiation strength of roughly 25%, which we think we'll be able to detect with a sensor. The magnitude of the signal will decline as you move through the flibe. You see on this plot here, you have the intensity of the blackbody radiation at the hotspot and where you might image it at the 2 different temperatures I laid out for you, and it does decline, but you still have a signal out at the part where you would image. And if you're actually designing this imaging system, you would very likely not image just at 1 micron. You would select 2 or 3 different wavelengths and image at those different places to get a more stable measurement. The next sensor I'm going to talk about is our Cherenkov sensor. Cherenkov radiation is probably quite familiar to the fission people among us. You see here an image of Cherenkov radiation in a nuclear reactor that's just down the street. It's this beautiful blue radiation. And what that's coming from is that when you have fast electrons in a medium that move at a speed faster than the speed of light in that medium, they'll emit sort of a visual sonic boom, which causes this blue light. Now this will happen in our flibe because we have a lot of neutrons, and those neutrons will produce gamma particles that will Compton scatter off of slow electrons and give you fast electrons, which will then produce this Cherenkov radiation. And we were not sure at first if this would be very strong or not. So we did a little bit of analysis using both MCMP simulations and some analytic calculations to see how strong the Cherenkov signal at our midplane might be. So you see on this plot here, this is the distance through the flibe tank. Here we have the midplane of the vacuum vessel, and here we have the edge of the flibe tank where you might be imaging. And this is the intensity of the Cherenkov radiation if you measured it at that point. So essentially it's line integrated from this point to wherever you are. So you see that it increases sharply at the beginning. That's because you have a lot of neutrons right by the edge of the device, and in turn a lot of electrons, which will give you a strong Cherenkov signal. As you move farther out, you don't have as many neutrons, and the absorption starts to dominate the behavior of the light you see, and you get some absorption, but by the time you get out to where you might be imaging, you still have a very strong signal. Probably order of magnitude 5 times 10 to the third watts per meter squared micron for a typical neutron production rate for arc. And this is very bright. For sort of reference, one of our team members looks at synchrotron radiation in plasmas, and this is roughly 5 times as bright as the signals he deals with. And this brightness will scale with the source neutron strength, so you'll be able to get some information about how big your source neutron production rate is by looking at the strength of the Cherenkov radiation. Now, I'm next going to talk about our reflectometer sensors. Now, to give you a bit of a refresher, we are running in ARC with a detachment front that is partway up our long-legged diverter, and this is inspired by work done by Umansky, and you see some of the results of his code here. And we have the log of the neutral density here, which goes in the opposite direction of plasma density. So like up here you have low neutral density, high plasma density, and here you have high neutral density, low plasma density. And you have the radiation power over here. And we want to have a good control of where this ionization front is and to be able to understand where it is. Now, the important thing about these ionization fronts is that they come with a very sharp step in density. You have here a situation that's slightly different than the one I showed you before. Here we have the plasma density, and we have an ionization front that's running down at the X point and not up the leg like I was showing you before. But you see very clearly here that there's a sharp change in the plasma density at the ionization front. And the idea of the reflectometer is to use that change in density to give you information about where the ionization front is. And we'll do this using 2 different types of measuring systems, one which has a coarse resolution and one that has a fine resolution. Now, this system is schematically diagrammed for you up here. So all of our reflectometers will come in through the FLIBE tank as waveguides, and these waveguides, being made of steel, are resistant to neutron damage, and they allow the source and the detector to be located outside of the FLIBE tank. And both the coarse and the fine systems will use an O mode density cutoff, and basically what that is that when you send a wave pulse through the plasma, it won't be able to propagate beyond a certain density, so it will bounce back off. Now, our coarse system is going to be a binary beam break system, which you see in these blue arrows up here. Those will just try to shoot wave pulses across the plasma. So when the density is sufficiently low, the wave will be able to go through. But when it becomes too high, it won't be able to pass through. And so by seeing where you get a signal across and where you don't, you'll be able to understand how the density changes on a coarse level. We'll also have a fine time of flight measurement system, which was recommended to us by Sung Yu. That is what you see down below. You'll have a wave pulse shot up the leg of a diverter, and it will bounce off the ionization front and come back. So by measuring the time of flight of that wave pulse, you'll be able to understand where the ionization front is. And it's important to note that this sort of system has actually been used experimentally before by a guy named Takahiro. And he was actually able to achieve a spatial resolution of 6 millimeters at a sampling rate of 0.4 megahertz. Now, our final set of sensors are magnetic sensors, which are placed outside of the FLIBE tank, as you see on these stars here. Now, FLIBE is very, very weakly conducting, so you'll be able to get a much faster magnetic diffusion time than you would if you had a metal blanket. And the slide after this, I'm going to talk a little bit more about that. But basically, this gives us very good response times. If you assume a 0.5% sensor sensitivity, you'll be able to detect a 2% change in plasma current in about 40 milliseconds, and vertical and radial displacements in 10 to 20 milliseconds. And these are comparable to our thermal detection times. Now, a lot of people are talking about building fusion reactors with metal blankets, and this sensor system shows why that is not such a good idea. Here we've run a simulation where we take the plasma current and we change it by 2%. And then we see how a sensor would pick that up at the outboard midplane if the blanket were made of FLIBE, and then if it were made of Inconel. And again, this is assuming a 0.5% sensitivity of magnetic sensors. So you see on this plot here, the dotted line shows where we've stepped the plasma current. And then the red line is the signal you detect with an Inconel blanket, and the dark blue line is with the FLIBE blanket. And you see the signal gets much, much more quickly to your sensors if you have a FLIBE blanket. In particular, it's about 40 milliseconds, but with a metal blanket, it's going to take at least half a second before you can pick up the change. All right, so we've now laid out for you our set of sensors on ARC, and these sensors are, of course, designed to respond to certain events that could happen in your plasma. So I'm going to take you through one of these events as an example of how our sensing system would work. In particular, we're going to look at a change in confinement mode. ARC is supposed to operate in I mode, but you could imagine that you lose the I mode. The sort of case that we're going to focus on here is that you somehow get a top-down magnetic imbalance in your configuration, which leads you to lose the I mode. You could also lose the I mode for other reasons, including an accidental impurity that flies off the wall, an RF problem. You guys can imagine many other circumstances, I'm sure. Now, when you lose your I mode, a lot of things will happen in your plasma. One of the first things is that you'll see a transient change in heat flux to your diverter. The magnitude of this and the sign depends on the sort of confinement transition you have, but in general, this is because you're either setting up or collapsing pedestals depending on what confinement change you're making. And this change in heat flux to the diverter will also lead to a change in the position of your ionization front. A little bit later, after an energy confinement time of around 1 second, you'll see a change in your neutron production rate. Now, our sensors will pick up these events. The first signal you're going to get is from your reflectometer after about 2.5 microseconds. And this will detect a change in the front position. This could be from the transient changes in heat flux that I outlined for you, but it could also just be from the top-down magnetic imbalance that caused your loss of I mode in the first place. A little bit later, around 75 milliseconds, you'll detect a change in temperature from your hot spots. And around the same time scales, your magnetic sensors will pick up a change in the magnetic equilibrium. Your Trankov sensors will be the last information that you get, because it'll take them about an energy confinement time of a second to respond, because they respond to the neutron production rate, which will change with the energy confinement time. Now, once you know that you've lost your I mode, you have to do something about it. So that is our actuator response. There are a few things you might want to do in this circumstance. First, you might want to just get back to I mode. In that case, you'd adjust the current in your trim coils to correct the magnetic problems that led to the loss of I mode in the first place. And this would take you about 50 milliseconds. You can also try to alter your RF power, either to change the current profile in your plasma or to heat it up more, or something like that. And that's sort of a slow knob because it takes about an energy confinement time for the plasma to respond. Now, you may occasionally be in a circumstance where you're very worried about your diverter melting, and you just want to do whatever you can to protect your diverter. And in that case, you'd probably do slightly more drastic options. And these might include a gas injection into the diverter. This would come from a plenum outside the FLIBE tank that you would suddenly open up and send gas into the diverter to sort of protect the walls of the diverter from melting. You could have a similar effect by just varying the exhaust pumping from the diverter to sort of choke the diverter on itself. So this is an example of how the sensors that I've just outlined for you would behave in one plasma event. We can also talk about other plasma events if you are curious, but this is just a demonstration of reasonableness for our sensor system. And with that, I'm going to hand it off to Hannah, who's going to conclude.
So in the last hour, we kind of ran you through all of the work that all 10 of us have done over the entire semester, and we think it's a lot. So with that in mind, we thought it would be expedient to conclude with a brief overview of the main points that we hit today. And so if you've been asleep for the last hour, it's fine. Just remember the things that I'm about to tell you. Well, yeah, so we think that we have successfully developed an exhaust system for ARC that would not only exhaust all the power produced, but we could actually, based on our heat management systems, increase ARC's power output up to 1 gigawatt. And so that's a grand conclusion that we came to based on these 4 main points here. First, we figured out magnetic equilibrium using superconducting coils that are all placed outside of the flibe tank. So that's a big win for us, because then the lifetime of our coils will be similar to the lifetime of the TF coils, which just makes everything easier. Second, we have this weird long leg diverter shape, and that the geometry helps us to reduce the heat flux down to manageable levels, and also gives us an order of magnitude reduction in the neutron flux, which was a big win for us when we were trying to figure out materials to use in these weird diverter legs. Instead of worrying about neutron properties and thermal properties, we could just focus on the thermal properties and the heat management down there. We also proposed some very complex geometries to use in the diverter legs that helped induce turbulence, that will really help deal with thermal stresses and just support the entire structure. Finally, we had some very novel sensing techniques that we proposed for this reactor that will help us detect perturbations in the plasma and then respond to them on a variety of timescales. So these are the 4 things that, if you remember nothing else, these are the 4 basic things that you should remember to tell your rich philanthropist friends about after today. And then when you're remembering these 4 things, there are a few areas that we acknowledge still need some definite work. And so the things that we would propose be looked into next. First, the complex geometries that we have referred to a few times. Basically, there's infinite variables that could be optimized, and that's a lot. So we have an idea of what bulk parameters we would like to see in like the cooling channels, and we think that we can definitely achieve those or even surpass those, but we would need more manpower and or more computing power to really actually optimize that. Similarly, we have an idea of what the material properties are that we would need in the diverter. And as Norma talked about, we think they're all achievable, and we have a few ideas about how we could get suitable materials by modifying the isotopes in TZM, maybe grading, making like a tungsten alloy. There's a few ideas that we would like to explore. We also need to get a better picture of some of the actual properties of flibe. There's a lot of documentation, as Libby said, on small samples, but when you have a huge tank full of flibe, there might be some different properties that we need to really study more. Turbulence, for example, in high magnetic fields in flibe would really affect some of our results. So again, that needs more studying. Similarly, the high temperature superconductors, we have them still in relatively high irradiation environments, and so we need to better understand how they're going to behave there. Fortunately, that is part of Brandon Swarbrum's thesis, so that information is coming soon. And then we would actually like to see some of these new systems implemented in a full non-fusion test cell. And also the weird long-legged diverter thing hasn't actually been built before. So we would also like to see them validated in ADX, which I guess if you're from PSFC, you're probably familiar with. Yeah, and so with all of this in mind, I guess we'll open up the floor now for questions.
Very good. So are there questions from the audience? Yeah.
So first of all, great job, everyone. Really impressive. And shedding some light on some very important questions that don't receive perhaps as much attention as you should. I wanted to ask about your coils inside of the flibe. So what kind of faults do you expect those coils to handle, and how do you plan to mitigate them? So, go ahead.
Can you repeat what kind of?
What faults do you expect to occur on those coils? How are you going to feed power to them? How can you assure that
Voltage.
what happens?
Yes, so on these coils, so we have 3 on the top and 3 on the bottom, so a total of 6. We did thermal stress calculations and thermal analysis, and we calculated that each coil is going to consume about 25 kilowatts from ohmic heating. We determined that 20 kiloamps is necessary to respond to a 2% change in the plasma. Concerning the voltage that we need to, I don't have it in mind, the voltage necessary for each.
Maybe describe the basic feature of the coil. What kind of, how many turns is it?
So it's going to be a 1-turn coil. So there was a trade-off here because like a 1-turn coil could create toroidal asymmetry, but we decided to stick to one turn just because of simplicity.
And the material is copper.
Copper, yes, we did everything with copper.
And I guess they're showing that flux on the copper isn't going to be a problem because of the fly.
Yes, so we put concerning that, so there is a sheath, so a shell of Inconel that is protecting the copper. We have
Structural. Yeah, so the copper at that high temperature is not structural.
Right.
So there you go.
Right.
So the Inconel is
So that's-
giving it structure.
Yeah, that's the design that we have for this copper coil. So for each of them, we have like a sheath of Inconel, 1 millimeter, and then just like strands of copper. So the sheath of Inconel is for structural support, basically. The flight is going to be at 900 Kelvin. There's going to be a high jump in the temperature due to the sheath of this shell of Inconel, and we calculate that the temperature of the copper is going to be around 1,000 Kelvin, less than that. Where the melting temperature of the copper is around 1350, so it's still below the melting temperature of the copper. So that's good.
Actually, Ted, to your question, because you're at such a significant fraction of the melting temperature, the effects of neutron radiation are going to be low because you essentially prevent as much damage as you create because it's so hot.
Yeah, and we also have to say that MCNP neutronic calculations that Jake performed showed that the nuclear heating on the copper at those locations is around 10 megawatts. And all the calculations, like the thermal analysis we did, were based on those numbers that come directly from MCNP, like from Neutronic calculations.
Ian?
So it's very nice that you're able to produce this long diverter with just a very few coils, but you seem to have focused on one particular equilibrium. And I wondered whether you've taken account of the necessity for example, the flux swing in the ohmic transformer to be accounted for. And if so, how did you do it? If not, well, what's the justification?
Right. So we didn't look at, for example, the startup phase with the flux swing and the ohmic transformer. I believe mostly in steady state, the current drive is primarily provided by lower hybrid current drive from the original ARC paper. But we were primarily looking just at steady state scenarios. We did look at changes in the plasma conditions or changes in the different coil conditions for using the trim coils to adjust the equilibrium. But again, it was primarily focused on steady state and not startup issues. That's definitely something that we need to look into the future.
I suggest it might go on the list of things to do.
Right. So the whole operation of startup and how we get from nothing to that geometry is definitely something that we need to address in a future work.
A question for Ian. So Ian, are you suggesting like a TSC simulation of
PM coil set during the discharge every
Not necessarily, but I just think you've got to take into account that if you're going to swing the ohmic flux, then you've either got to screen it out or you've got to adjust the currents in all the coils, and that's going to change the shape of the diverter and so forth. So you need a series, at the very least, a series of equal differences. Convince yourself that there's an excess of it. Doesn't have to be quite so grandiose, although we did that to see one. Right.
Joey, you have a question?
Yeah. What temperature were you assuming the superconducting diverter coils were running at, and what current density?
I believe it was 30 Kelvin. I believe it was 30 Kelvin. And the current, I don't remember the critical current density off the top of my head, but those were calculated based on the poloidal and toroidal magnetic field contributions and the critical current density in the most recent YBCO tape that has been produced.
It was a couple hundred amps.
It was like 500 amps per.
Well, no, but the one that we used was like a couple hundred amps per square meter. I can't remember.
I don't remember.
It's in the calculation.
Yeah, and I guess the other caveat on that is those coils assume 15% actual tape in the coil, and the rest of that is structure and cooling. So if and it turns out that like the structural loads are actually pretty low, so that number may be able to push up slightly to something like 20%, which would then reduce which would allow us to put more current through without pushing up against the critical current density.
Can I have a follow up on this one with the copper? At 1000 K, it's going to be really dead soft, and I realize you're using the Inconel sheet for the structure, but it's just going to be butter in there and highly resistant. So I assume you use the resistivity at that temperature.
Yes. It's we put the resistivity both of the Inconel and the copper at that temperature. So everything is based on at the temperature of.
There was a fun point in the class when we considered letting it melt and having a molten copper. we backed off of that. Any other questions?
Did the thermal structural analysis consider any cyclic effects, or was it just looking at steady state stress profiles?
Yeah, we for the class we were primarily focusing on steady state profiles.
Can you comment though to something like ARC with respect to cyclic stress?
Yeah, so ARC is designed again to run steady state for extended periods of time. Again, we have lower hybrid current drive, so we're not limited by the ohmic transformer. And so the design is supposed to last like 1 year at steady state.
Charles, no questions about the fly?
Well, the heat transfer, how far did you go into irradiated heat transfer, given the fact that everything here is so hot? You've got that T to the fourth that wants to radiate heat, and it sort of make an equilibrium temperature. Go very far into that in terms of the heat transfer calculations on fly.
So are you specifically talking about the diagnostic side of things where we're trying to look through this radiating body, or are you talking more in terms of the total global heat transfer perspective? From the global heat transfer perspective, it was a power balance case. So the temperatures we achieved were simply based on the total power input and output. When it comes to the diagnostic side of things, we actually incorporated into assuming that some sort of absorptive and radiative effect of the fly as you're looking through it, because of the black body radiation at that temperature.
Do the shrink up idea is a really interesting idea. Is that done in fission reactors to monitor power?
Not that I know of. I don't think fission reactors actually look at the chunk of and use it.
Any idea why not?
They have a lot easier ways to do it than that. I think is the simple answer.
Well, the shrink off radiation is from the spent fuel, not the. My understanding is anyway, it's not in the
Miklos had a question, I think.
Yeah, you didn't say much about the central solenoid. Maybe it goes back to the ARC design. I don't know. Is it monolithic or is it segmented, or it just either? Originally it was monolithic, and then physicists criticized it. And then it got segmented into 5 sections, causing increase of complexity and so forth. I'm just wondering what's yours.
So This was based on the design, which where we didn't consider a central solenoid.
Yeah, we didn't do
segmented.
we didn't do any work.
They did no work. I cut off work actually. It was my fault because I cut off work at basically the inner leg of the fly tank. They do not consider the central solenoid or the TF coils. Those are taken together.
In a Comey, it was modeled as a series of filaments.
Yeah.
But yeah, the actual design.
I mean, it was an equilibrium model, but it was what it was used in art originally. They did not play. It is segmented. Yeah.
So, and a comment, I don't think we need to worry about isotopically pure molybdenum, given that you have about a 10-ton Inconel highly activated structure nearby. So probably need to go right to the column. One question I had about flow was it sounded like you have one pump and then tank and all, and all the coolant. That was great. How do you ensure you don't have stagnant channels everywhere? That would be critical if you had a hot spot that would develop and then simply you have a positive.
Yeah. Or stagnant flow in the tank, you mean? Or
Just anywhere. I mean, how do you, if you have one pump that's a giant complicated, I grew up on a river.
Yeah. Yeah, so they're actually
you know, you have flow made it from other direction, but you have stagnant flow. You have things that gather in it. How do you ensure you don't have problems with flow first?
Yeah, so one thing we didn't explicitly talk about today was like including sets of manifolds around the device. So we have like 18 toroidal sections, we have these colloidal channels, cooling channels throughout the whole vacuum vessel, and incorporating like overlapping manifolds that would hopefully ensure that if one pump would fail or something becomes stagnant, a pipe, then another pump could take over the response, you know, for that extra. As far as like eddies in the like fly tank itself, we didn't really like look into that too much. Hopefully we're just assuming that it will like mix all together. But yeah, I don't know.
It's a very good question. Actually, it was, if you recall from the first ARC design, there was some assessment of this, but it was very difficult to do because it actually came into limitations in the computational capabilities as well too. Similar as to what we ran into in this class. There was a true appreciation for the limitations of computational power, even in these ones. Yeah. Which is, I think, by the way, the motivation for the idea of doing this in a non-nuclear test tank, and do this at some kind of scale that makes sense, that you actually understand the flow patterns. Or you don't actually, you can replace the heat sink, or sorry, a heat source in many ways with something else, and get at these problems. So that's one more question.
What was the motivation for doing the Cherenkov based fusion power model? And maybe it's just a lead-in, right? Every tokamak around the world currently puts a bunch of thermal neutron detectors in the cell and simply looks that way. I was curious what the motivation.
Right. So first of all, I guess the inspiration for this was just the realization that we would have this strong radiation there, and maybe we could get some information from it. What I presented was a very simplified Cherenkov radiation system, which I presented as just being a way to detect neutron rate. As you get more experimental experience with such a sensor, you might be able to use it to detect other things, perhaps. Maybe you could get some information about the makeup of your fly based on like the strength of Cherenkov radiation. If you have like something happening to your fly, but it was not clear to us that would absolutely be possible, but you could imagine using the sensor for other things like that, and this would be a starting point for that. Do you want to add?
I was going to make a comment. One thing
it's actually, to think about it, it's actually the image that you get, and we didn't have time to really assess this. Essentially, direct measurement of neutron transport in the fly.
Well, I was going to make one comment, which was that one of the things that, for instance, ITER is going to have a lot of problems with is calibrating its neutron detector, because the flux that they can get out of, say, DT generators that they put in the vessel is so low. And so if you had an optical system which can be sensitive down to photons instead of a couple kilowatts, you might actually have a system that is much easier to calibrate with small sources instead of going to heroic efforts like ITER is with modeling and DT generators. That's something to look into, because that has a really nice side effect.
Okay. I am going to have to get going, so I think I'm going to have to cut off questions there. So let's thank the class.